Hi, my name is Vukašin Karadžić and I'll present you our paper titled Populating the Zoo of Racket Pseudo-Random Permutations. This is a recorded version of the talk that I gave live at Asiacrypt in Guangzhou. In this work, together with my advisor Jean-Paul de Gabriel, we revisit the definition of racket pseudo-random permutations and provide new constructions. I'll start by giving you some background on racket pseudo-random permutations and their applications, since I assume not many of you are familiar with the concept. A racket pseudo-random permutation, or RPRP for short, is a security notion for variable length equal ciphers that we introduced at last year's crypto. For variable length equal ciphers, there are two standard notions. The first one being the PRP notion, where the adversary has full access to the enciphering algorithm, and the other being SPRP notion, where the adversary has full access to both enciphering and deciphering algorithm. And by the way, with PRP and SPRP, I denote here the two equal versions of the notions. The RPRP notion lies right in between, and there the adversary has full access to the enciphering algorithm, but only partial access to the deciphering algorithm. Let's look at the details of the definition. Syntactically, an RPRP is a variable length equal cipher defined over a split domain 0, 1 to the n times 0, 1 star, meaning the enciphering algorithm takes in the tweak t and the input XL/XR, where the XL is a fixed sized n and XR is a variable length. The real world in a security game looks as follows. The adversary has access to the encipher and decipher oracle, but with two restrictions. First, it cannot forward while from the encipher oracle to the decipher oracle, and second, it cannot repeat while as an input to the decipher oracle. We provide the adversary another way of querying the deciphering algorithm, and that is via the guess oracle, where, in addition to the t, while, and yr, the adversary also needs to provide its guess xl prime. The guess oracle then internally deciphers t while yr to obtain XL and outputs only a single bit of information, and that is whether the internally deciphered XL is equal to the adversarially guessed XL prime. In the ideal world, we replace the two equal cipher with a two equal permutation and make a small simplification in the guess oracle such that it always returns bot. This simplification in the guess oracle imposes an additional restriction, and that is the adversary cannot query inputs to which it already knows outputs to. But why this complicated notion? Well, RPRP being a weaker notion than SPRP implies that we can build more efficient schemes, but the notion proves to be still strong enough for realizing many useful applications, as I will show you now. The first application shown in our work from last year is building AAD schemes using the classical encode and encipher paradigm due to Velare and Rogoway, but with RPRPs instead of SPRPs, which was the original requirement. The first transform that we presented was the ET transform, where the encryption algorithm works as follows. First, the AAD input is encoded into the TXLXR, and then that is ran through the enciphering algorithm of the RPRP to obtain the ciphertext. We showed that the ET transform yields misuse resistance AE. Because of the asymmetry between the enciphering and deciphering algorithm in the RPRP definition, it was also natural to consider using the deciphering for encryption. And that is exactly what was done in our second transform called ETD. Here, the encoded input TXLXR is ran through the deciphering algorithm to obtain the ciphertext. We showed that the ETD transform yields RUP-secure AE scheme. In addition, each of these transforms can be instantiated in both nonce-based and nonce-hiding AAD syntax, leading that one has 4 AAD schemes using just a single RPRP. The next application shown in previous paper is using RPRPs to build order-resilient channels like Quick or DTLS. As an intermediate stepping stone in this construct, we use the so-called nonce-DAD in a modular way. Here, the decryption algorithm takes as an input a set of nonces instead of a single nonce, and upon successful decryption, it outputs the decrypted nonce n and message m, where the decrypted nonce n is from the nonce set provided to the decryption algorithm. Order-resilient channels operate over unreliable networks like UDP, so a receiver needs a way to recover correct reordering of the packets received. That is done by having each ciphertext carrying a packet number associated with it. It turns out that in this construct, the decrypted nonces exactly correspond to the packet numbers of the channel. Using this RPRP-based approach in building order-resilient channels automatically caters for encrypted packet numbers, and one gets more compact ciphertext than, for example, the nonce-hiding transforms by Bellare and Tuckman. The third application of RPRPs is in Tor's onion encryption. It's been known for years that tagging attacks can compromise privacy in Tor network. One way to prevent these attacks is by replacing each encryption layer with a white block cipher that is SPRP secure. However, at Real World Crypto last year, it was shown that using SPRP is an overkill, and one can achieve the same with RPRP white block cipher. In addition to the protection against tagging attacks and the performance benefit, the RPRP-based approach also offers forward security, and its performance is competitive to the Tor's current onion encryption. We now come to our first contribution in this work, where we revisit the rugged pseudo-random permutation definition. If we examine the proofs of the encode and encipher based AAD schemes I showed you earlier, we note that the ETE security proof does not make any use of the decipher oracle, and similarly, the ETD security proof does not make any use of the guess oracle. We also found a similar situation in other applications. That made us revisit the RPRP definition, and we defined two refined notions. The first one being RPRP-D notion, where we drop the access to the guess oracle, and the second one being RPRP-G notion, where we drop the access to the decipher oracle. We then studied the relations between the original notion and the two new notions, and showed that the RPRP notion is strictly stronger than both RPRP-D and RPRP-G notion, and the RPRP-D and RPRP-G notion are incomparable, meaning there exists a constructions that satisfies one notion but not the other one. By introducing these new notions, RPRP-D and RPRP-G, we minimize requirements for every application, and in addition, because RPRP-D and RPRP-G are weaker than RPRP notion, we also opened avenues for new constructions. We note that achieving RPRP notion is still desirable because one can get both RPRP-D and RPRP-G security with a single construction, which is exactly what is needed in any encryption use case, where the RPRP-D secure construction is needed for the forward direction and RPRP-G secure construction is needed for the backward direction. Having now these refined definitions, we turn to look at the constructions. In our previous work, we had a reviewer rightfully noticing that RPRP definition looks a bit artificial. And that was substantiated by the fact that only a single RPRP secure construction was given in that paper, called the UIV. This could lead one to wonder, first, whether the notion has been tailored to this single construction, and more importantly, was introducing all this formalism worthwhile, if there is only a single construction satisfying the notion. In this work, we answered these questions in a manner positive for RPRPs by giving three new constructions. One that is RPRP-D secure, one that is RPRP-G secure, and one that is RPRP secure. The first two constructions are based on a 3-round unbalanced Feistel. We call the first one the ECE construction, which stands for expand, compress, expand, where we have the first and third round being expanding one, realized using an expanding PRF FE, and the second round is the compressing one, realized using a compressing PRF FC. We showed that ECE is RPRPD secure, but not RPRPG secure. The other construction is the CEC, which stands for compress, expand, compress. And here we have the first and third round being compressing one, and the second round being the expanding one. We showed that the CEC is RPRPG secure, but not RPRPD secure. These results are interesting for at least two reasons. The first one being, we show that from a theoretical perspective, a 3-round fight that achieves a cipher-based notion stronger than PRP, which is a result by Lubin and Rakov dating back to 1988. And from a practical perspective, although the 3-round look inefficient, one can instantiate it fastly using the recently introduced DEC functions by Bakuietsi and co-authors. We now turn our attention to our last construction, the HEC construction. For the HEC construction, we use the HCTR construction by Wang, Feng, and Wu as a base. In the HCTR construction, the first and the third layer are realized using the almost XOR universal hash function H, and in the second layer, we have a block cipher call followed by a counter mode on the right for the variable length part. The first and the third round in the HCTR construction are there to prevent repeating inputs to the block cipher on the left. Recall that the RPRP game restriction says that one cannot repeat YL to the deciphering algorithm. Then it seems that if we remove the lower layer, the RPRP restriction will still enforce the non-repeating part on the left block cipher, and that we would get an RPRP secure construction. However, the resulting construction is not RPRP secure, as I will show you with this simple attack. The adversary queries an arbitrary input to the enciphering algorithm and gets YL1, YR1 as an output. We can then express the hash of the T and XR1 as the following equation. The adversary then takes in the first block of the XR1 and of the YR1 and XORs them. The XOR of the two blocks is exactly the output of the first block cipher call in a counter mode, and the corresponding input is the IV1 XOR 1. Then the adversary makes its second query, which is a deciphering query. For the left input, it puts exactly this XOR of the two blocks from the first query, and for the right input, it leaves YR1. Then one can express now the hash of the T and XR2 with the following equation. The adversary then can take the XOR of the hash of T XR1 and the hash of T and XR2. The IV1, which is the unknown in both equations, will cancel itself out, and we are left with only a single unknown, which is the hash key H. The adversary then can extract the hash key H, and with H, it can mount a simple distinguishing attack. We circumvent this problem by introducing a masking key KC, and that's how we arrive at our construction HEC. The difference now between the HEC and the original HCTR construction is that we have one less pass over XR in the HEC, which makes it a more efficient construction, but we have one additional key, luckily with no key scheduling. And the additional key is exactly this masking key KC. In the paper, we prove using the H coefficient technique that the HEC is RPRP secure up to a birthday bound. Lastly, we looked at the techniques of extending the left domain of certain RPRP ciphers, and the motivation for that was the following. Looking back to the order resilient channel use case, if one inspects the integrity term in the security bound of the secure channel, it looks approximately like this. We have some V, which is a channel parameter, times Q, which is the number of forgery attempts, and one needs to be able to allow forgery attempts in order resilient channels, and times 1 over 2 to the n, where n is exactly the size of the left domain of the RPRP cipher. N usually corresponds to block size B of some tweakable block cipher, which is exactly the case, for example, in HEC construction, meaning n will be 1 to 8. And in some certain special use cases, both V and Q can be large, for example, up to 2 to the 64, so V times Q over 2 to the 1 to 8 may not be enough for some reasonable security. And then we took a look how can we extend the size of n. The main scheme we looked at is the UIV scheme from previous work. Here we're interested in how can we replace the tweakable block cipher of block size B with a tweakable block cipher of block size something greater than B. The first way is to double the domain from B bit to 2B bits. For that, one can realize the 2B bit tweakable block cipher E tilde star using a classical domain extender by Coron and co-authors that we call CDMS. Here, CDMS uses a B-bit tweakable block cipher E tilde to build the 2B-bit tweakable block cipher E tilde star. The second approach is to extend the domain with S bits where S is less than B. Here we instantiate the E tilde star using the LRW2 construction by Liskov, Privest and Wagner, and the E tilde star is realized using an AXU hash function H with output size B plus S and a block cipher E star of block size B plus S. Furthermore, we then instantiate the block cipher E star using the LDT construction by Chen, Manning and Nandi, and here the E star is realized using just a tweakable block cipher of block size B. What about the constructions that we presented in this work? Well, for ECE and CEC, extending the left domain should not be too hard, usually. For example, one just needs to adjust the input or output size of the expanding and compressing PRF. That should be especially easy with the DEC functions that I mentioned earlier in this talk. For HEC, we see that the left and the right part are not independent since they are keyed with the same key, so a black box solutions that we had for UIV is not possible, and we leave it as a topic for future work to find dedicated domain extenders for HEC. To summarize, in this work we refined the RPRP abstraction and introduced the ECE, CEC, and HEC constructions. The effect of these new schemes is big because they lead to new various AAD schemes, they lead to new non-set AAD and order resilient channel schemes, and to new onion encryption schemes. The main takeaway message of this talk would be that the RPRP abstraction and RPRPs are indeed natural. Thank you for listening. If you have any questions, feel free to write us an email, and you can find our emails on the full version of this paper, which is already on ePrint.